You know when you drive past one of those massive industrial plants and it just looks like a totally chaotic tangle of metal and pipes? Well, what if I told you there is literally zero chaos involved? Welcome to The Explainer. Today we are decoding those massive three-dimensional highway systems hidden right in plain sight. Think of a processing plant just like the human body. It needs a way to pump its vital fluids, chemicals, steam, water, and gas to all of its essential organs. That is exactly how pipe rack design works, and today we're going to unpack the brilliant engineering behind it. Okay, let's kick things off with a foundational concept straight from our engineering sources. A pipe rack is the main artery of a processing unit. Think about that for a second. Just like arteries pump lifeblood through our own organs, these structures are absolutely vital to a plant's survival. They are the central nervous and circulatory system all rolled into one. And because of that, there's a hard and fast rule in construction. The pipe rack has got to be erected first. If you wait, the whole area gets completely obstructed by rows of heavy equipment. You literally have to build the highway before you can build the city around it. So let's get our terms straight. What exactly is a pipe rack? Well, it's a structural system usually sitting smack in the middle of a plant that connects equipment with process and utility lines that simply cannot run through the adjacent areas. We are not talking about some temporary metal scaffolding here. No way. This is a meticulously planned, permanent arterial system governed by incredibly strict laws of physics, thermodynamics, and spatial geometry. Here is our blueprint for today's explainer. First, we'll map the pipe highway. Then we'll look at shapes and structures. After that, we'll slice into what's called the layer cake, go over the golden layout rules, and finally look at how engineers design for the future. Let's get right into it. Section 1. Mapping the pipe highway. Setting the foundation. Every massive, multi-million-dollar plant starts by bringing some serious order to the initial chaos of a new layout. So how do engineers even begin tackling this? Well, they follow a really rigorous linear progression. Step 1. They generate a line routing diagram based on super complex schematic data. This establishes line sizes, materials, and operating temperatures. Once they know exactly what needs to move, step 2 is establishing the physical rack width, figuring out how far apart the supporting columns need to be, and determining how many levels are required. And finally, step 3, they work out a typical cross-section. All of this happens on paper and screens way before a single drop of steel is ever poured. Moving on to section 2, shapes and structures. It's actually wild to realize that pipe racks physically dictate the entire footprint of the plant, bending and shaping themselves based on site conditions and road placements.
Let's look at the first basic shape, the straight-through yard layout. A straight rack configuration neatly splits an operating area right down the middle. It's a highly efficient design that lets process lines easily enter and leave from both ends of the plot. Honestly, it's the most straightforward, literal highway approach you can possibly take.
But what's really fascinating is how this artery adapts when things get in the way. Take the L-shaped layout. When roads or control houses block a straight path, the main artery simply bends. This allows it to easily service process equipment on both the north and east sides of the facility without skipping a beat. Now, what if you've got a massive centralized block of equipment? Well, that requires the T-shaped layout. This specific design gives you 3 distinct points of entry and exit. It lets the piping efficiently branch out and wrap around all that complex, densely packed machinery without creating a massive logistical bottleneck. And finally, we have the U-shaped layout. This is kind of the ultimate wrapper. It almost entirely encircles the facility, which allows the pipeline network to enter, exit, and service all 4 sides of the plot plan. It's an incredibly comprehensive structure, usually reserved for highly complex, really sprawling processing units. All right, stepping into section 3, the layer cake. We're moving out of that flat 2D footprint and looking up into the vertical 3D reality. Essentially, a pipe rack is a multi-story highway managing very specific types of traffic. When you examine a cross-section of this highway, the level of organization is just incredible. Think of the bottom tier like the slow lane for heavy 18-wheeler trucks. Predominantly, your heavy process lines, like the massive pipes carrying dense cooling water, form this ground floor. Meanwhile, the lighter utility lines, hot process lines, and instrument cables, they speed along the upper tiers. Engineers systematically separate the hot lines from the cold lines across these different levels, which is absolutely crucial to safely manage thermal extremes. And then, right at the top, there's what we like to call the penthouse tier. Our sources point out a very specific rule for the very top of the rack. Relief headers must be located completely above the top level. But why? Well, it all comes down to gravity. In an emergency, these lines need a totally clear downward path to drain volatile materials safely into a blowdown drum. You are quite literally designing from the top down just to let gravity do its job.
Which brings us to Section 4, the Golden Layout Rules. This is where we dive into the strict, unbreakable rulebook that dictates exactly where every single pipe is allowed to sit.
The thing to remember here is that engineers aren't just tossing pipes wherever they happen to fit. They follow incredibly strict guidelines. For instance, if you have flanged valves on two pipes sitting right next to each other, you actually have to stagger them so they don't physically bump into one another. Also, massive lines, we're talking anything over 14 inches, have to be placed near the supporting structural columns to reduce the bending weight on the horizontal beams. Oh, and my personal favorite rule: if a pipe needs to change direction, it must also change elevation, using 90-degree elbows to weave through the rack without crashing into the other lines. It's like a giant high-stakes puzzle.
This actually brings us to a major layout pitfall, one that really separates the novices from the experts. You might think placing a heavy pipe dead center over a vertical structural column is the strongest, safest bet, right? Well, actually scratch that. It's the wrong location. The right location is offsetting it slightly. Why? Because if you block the dead center of that column, engineers can never extend that steel beam upward if they ever need to add another level in the future.
And speaking of vertical space, consider this number: 7,000 millimeters. That is roughly 23 feet of required overhead clearance above main roads inside the plant. Think about that for a second. Engineers have to raise thousands of tons of steel and fluid incredibly high into the air, specifically so that massive maintenance cranes can safely pass underneath the rack. Literally every single inch of clearance is meticulously calculated for the heavy machinery operating down below. Finally, we arrive at Section 5, Designing for the Future. We're going to look at a somewhat counterintuitive secret of industrial design, which is the absolute necessity of paying for space you aren't even using.
25 to 30%. According to strict engineering guidelines, any good pipe rack design deliberately leaves up to a third of its clear width completely empty. I mean, when a new plant is built, you will literally see wide open bare steel right next to a densely packed row of pipes.
Now, you might be wondering, did they just forget to put pipes there? Not at all. This isn't an oversight. It's a deliberate economic and physical choice. They are anticipating the unknown. You see, metal expands and contracts wildly based on temperature. If a hot pipe expands and there's no empty clearance next to it, it will literally crush the pipe right beside it. Plus, leaving up to a third of the rack empty guarantees the plant actually has room to add new lines and adapt to future unit growth decades down the line. It's future-proofing at its finest. Which brings us to the end of our structural journey today. So, next time you pass one of those sprawling industrial plants, will you just see a chaotic tangle of metal scaffolding? Or will you see it for what it truly is, a living, breathing arterial highway system? Once you understand the hidden rules, the layer cakes, the golden rules of placement, and those deliberate empty spaces, that chaotic maze transforms into an absolute masterpiece of engineering. Thanks so much for exploring this with me, and we'll catch you on the next explainer.